This is when you actually access a pointer in memory. The second one is a instruction TLB. Basically, this is for quickly executing code. So the assembly to actually invoke the process of loading memory into the data TLB is just to dereference a pointer. That'll cause an entry to be added. For the instruction TLB, it's a little bit different. You have to dereference that memory, copy a return value into that, so basically come back from where you came, and then do a short call. And that'll populate the instruction TLB. This is just like executing code. So we wrote our tool called Saffron, and what Saffron does is it implements a hybrid page fault handler. And again, this was inspired by Ollie Bone by Joe Stewart at DEF CON 14. We really like this, so thank you, Joe. We only implemented this for 32-bit Intel CPUs, and basically we replaced the Windows trap handler. And essentially what it's doing is logging memory access. So we have this diagram of how things happen. The first thing that happens is that we start with a virtual address, and the hardware tries to resolve it. At that point, if it's not valid, it kicks it over to the operating system, checks to see if it's in the disk, checks to see if permissions are correct, and if not, it returns the address or it returns the error. So our code fits right into that permissions code. And if any of you are looking to translate it into, I believe this is Mandarin, here's a pre-translated version of the slide that we found stolen. They were nice enough to translate the paper, but not our names.
Or even copy our names in English.
Yeah, or even, I don't even. Okay, so as far as the actual software architecture, the page fault will come in on this left of the interrupt descriptor table. Saffron looks at it, determines whether it's something that we actually care about, and if we don't care about it, we kick it over to the Windows page fault handler. Otherwise, we talk to our user mode process that's actually monitoring this. The particular bit that we're overloading to cause the page fault is the supervisor bit. Basically, what we want to do is find the process's memory and mark the supervisor bit on everything inside of there. And then we want to invalidate the page inside the TLB, which is basically says clear your hash table of all your entries. Actually, if I could turn off caching on an Intel CPU, that'd be nice too, but I can't. So if anybody knows how to do that, please talk to me after. The next thing is that the tricky part is finding all the memory. First technique is to start at 0 and go all the way up to all Fs. And basically what you do is you can also iterate through all the pages, or you can look at the PE header and then just go to all the sections and mark those. So again, we're determining if we're a watch process or a piece of malware that we want to unpack. First thing we do is we unset that supervisor bit, allow it to be loaded inside of the data TLB, and then apply the supervisor bit again so we can watch it. The method that you use to watch for executions inside of the memory is via the iTLB. So Jamie Butler and Sherry Sparks call this the TLB desynchronization. So since there are two TLBs, you're going to get a separate page fault when the code tries to execute inside of there. And what you're going to do is you'll mark that as the original entry point, and that'll send a signal to our monitoring program to actually dump the memory. The results of this, we can see the reads, writes, and executes. We can tell what they are, which is sort of nice. We can see what's being executed. The reads and writes are transparent. The problem is that you can only see for each individual page, but as we'll show in the demo, it's actually pretty fast. And it's pretty accurate too. So it solves a lot of problems for us. So the SEH decode problem, where it's causing issues with the actual SEH process inside of Windows, is just completely sidelined. Memory checksumming, the process, we don't actually touch the process memory at all. So we get good dumps across this. Some caveats. It's Windows XP Service Pack 2. I haven't even attempted this on Vista yet. You have to turn data execution prevention off. I believe that Microsoft uses a similar method to prevent executions into code segments, but that's just me guessing at this point. The other one is single CPU. You have to disable multiple CPUs in the BIOS, and this is purely a coding problem. And it's 32-bit only. We don't really care about 64-bit yet because there's not really much 64-bit malware.
Has anyone seen any 64-bit malware yet? I haven't seen her.
Yeah. Okay. I'm sorry, what was it?
I was just joking. I said they're still working on 486s in Russia.
Oh.
Yeah.
What are you implying there? Okay, so our big announcement is that magically it works on VMware 6, which hopefully we'll be able to demo for you here. But if not, we have a movie. We watched Dino's presentation yesterday, and we're peer pressured into doing a live demo for you.
Yeah, it's just ShmooCon. Got to do a live demo.
Some other caveats is that you either have to have real hardware or VMware 6 or higher. Older versions, if you read the paper that they published in ASPLOS,
Asplos?
the VMware engineers actually described their method, and they're playing the similar sort of tricks with the TLB that we are. So it breaks our stuff. So real hardware, as far as real hardware, you got to take proper precautions, and that's using deep freeze or DD or anything like that. And also we found that you can't have a kernel debugger attached because the Packer T-lock still detects the kernel debugger, which is really kind of neat of T-lock. But anyway, if you just detach the FireWire debugger, it works great. Okay, so we'll try and do a live demo here.
This was working, and then it wasn't working, and then it was working again. So if not, we have a video where it definitely works. All right, so what we've got here is a VM, and it's loaded up with Saffron. We have a few samples of NetBull that are packed with different packers. We'll try T-lock, because it's one of the more complex ones. So what I've done here is put it in PID to sort of prove that it's actually packed with T-lock. Oh, yeah, sure. You guys see that okay? Yeah, I know it's not going to be great. Okay.
You can also, there's plenty of room up here if you'd like to.
Yeah, so we're using this tool, or actually, why don't you describe it? You tell me what to do, I'll run it.
Okay, so basically what we have is a kernel driver here, and we want to install it into memory. So we use the InstVRV, which we learned from Jamie Butler's rootkit book. We've looked at PID, determined that it's T-lock, and if we copy the original file over to IDA, we'll let that chug there for a little bit. Basically what we're going to see is that you get this warning about imports being destroyed, so we're going to click through that because we have no fear. And it's going to continue going, and we get this nice function which looks like a whole lot of nothing. There are no functions available. The imports are pretty much non-existent. The strings window doesn't have anything real useful there. So the conclusion is that this is a packed file. So we're going to go ahead and close this. And the next thing we're going to do is go to Saffron, which we have a command line for, and we're going to cross our fingers and go ahead and hit that. Okay, so we get a candidate address here, and it looks like
it crashed.
Looks like it was a good demo, and it crashed. So we tried. I'm sorry, but we do have a demo of it running on. It's still a little picky about raw hardware. So what I'll do is.
Want to see me blue screen it?
Yeah, I don't think that's necessary. Okay, so. Sorry about that. We sort of expected this to happen and we tried it about 400 times yesterday, marveling at the magic that it was. And
there's still something going on that we don't quite understand about the way VMware interacts with the TLB, which makes this unstable on VMware. On raw hardware, it's completely stable.
Yeah. Okay, so this is a video of raw hardware. And basically, we're going to